long time ago, I remember we went very quickly over normalizing flows, and perhaps we can give a recap at a slower pace. So the main thing to remember about normalizing flows is the intuition. Well, it's not the main. Well, it's important to understand the intuition, and after that, things become not like a bit simpler. So the intuition here is that if you have a continuous distribution, you can convert it to any shape via the change of variables formula. And this is important because in reality, our data are more likely to look like as they become from such a distribution rather than such a simple distribution. And importantly, we don't even know parametrically how the data look like, right? Like that's what we're looking for. So in a way, we're looking for something that is as flexible as possible, without requiring to give an explicit, prescribe an explicit type of distribution. So normalizing does exactly that. That's the great thing about it. You're starting from something simple, something that it's easy to evaluate, it's easy to sample from, and so forth. So it's a canonical distribution, and you convert it to whatever you want, like whatever is needed for your data, without having any particular requirements as per the type of type of distribution you get in the end. That will be intractable to sample from or to evaluate it. So by doing this multiple times, you can easily get any type of distribution you want. Like, is that clear? Like, intuition is clear? Okay. Yeah. So the change of variables formula is this integration by substitution. Or basically our initial density. We can replace the g of x inside with a u random variable and sort of normalize it with the volume of the probability change, of the change of the probability distribution. So px pz, zx is our probability distribution. So x is like, for instance, the distribution of our data. Z is the distribution of one layer of a neural network on top of the data. And this term is to sort of normalize, to canonicalize the change, because the probability space changes. And when you apply it to the logarithm, it's simple summation in the end. And intuitively or geometrically, this looks like as follows. So if you have one distribution, p of x, that's your, like, let's say the simple one that you know that you can how to sample. Like, for instance, it might be uniform from 0 to 1. You know its volume, and then you have to account for the volume change here. And this is like what normalizing flows does. Like, the determinant fixes this real volume. Okay. So this is what we more or less discussed anyways. Yeah, and normalizing flows are basically this change of variable formula applied multiple times. So then you can go from a very simple distribution to much more complex ones very easily, and importantly without having any hard requirements, without having to know the type of distribution you get in the end. It's a completely data-driven approach to obtain any type of distribution in the end. Of course, this comes with its own limitations. It has to be invertible because of the here. We have to have neural networks now that are invertible. find easily the inverse. That's not comfortable. We also have to have scalable, easy, good ways of discovering, of computing the Jacobian. So the first order derivative of the function with respect to the input. That again can be quite complex because, as you will see here, basically z and x have to be the same dimensionality, right? You're just taking one density and you're like pushing it, you're changing the shape, but the size of the space, of the probability space, remains the same. So if you've got here an x which has, I don't know, like thousands of dimensions, your z will also have thousands of dimensions, which means when you have to compute the Jacobian determinant, that's not going to be necessarily easy. Ideally, you want to have a easy to compute closed formula. And we discussed some example transformation you can have here. Now, what is important to realize or to understand is that originally normalizing flows were proposed in the context of variational autoencoders. We have the, I'm not sure if I have the plot here, but so basically this, like this process, this normalizing flow, would substitute the prior of a VA. The idea, the basic idea, was that a Gaussian prior, like here, might be too inflexible, might be too crude for real data. So ideally, we would like to have priors that are much closer to the real data so that you can sample easily from. But how can we know what are these priors of complex data? Well, if you put a normalizing flow here, pipeline, instead of just a Gaussian, then you just simply automatically learn your prior, which is optimal for your data. So that was the main, like the first use of normalizing flows. Afterward, people, like researchers, proposed to use normalizing flows for computing directly densities. So this is your image space in the end, and this is your, let's say, initial prior. But originally it was not proposed for that. It was for, like, for modeling better the prior of the latent. Now, why I'm saying this? Because both are called normalizing flows in practice. However, it might be a bit confusing because, okay, initially, so from Rezende and Mohammed, when they proposed it for normalizing like to replace, improve the priors of VAs, they proposed basically two transformations: planar flows, planar flows and radial flows. For planar flows, the transformation is simple. You're adding to the input of your neural network a simple nonlinearity. And H is an element-wise nonlinearity. The log determinant is easy to compute. It's just this like absolute, like the norm of this transformation. So that's easy to compute. However, this transformation is not easy to invert. And for when you're having normalizing flows for your VA priors, this doesn't really matter because in the end you got the Gaussian to sample from, so they were using it only in the one direction in practice for their paper. However, it's not easy to sample from, because to sample from you have to go the other way. However, they didn't care about that because they were not sampling from this space anymore. In their case, they were just sampling using the Gaussian for the VA. However, you know, like that was the original transformation proposed. It's a planar flow. It's easy to compute. The log determinant of the Jacobian is easy to compute. Easy to compute the forward pass. Not so obvious how to compute the inverse. However, for the original paper, that was not needed. And the same for the radial flow. All right, I got here. So here, That was where the normalizing flow was put. Yes?
Maybe more of a practical question. The Fs or the neural networks, are they parameterized all by the same? Are all the F1, 2, 3 till n? Are they all parameterized by one network that just feeds in like for the diffusion model feeds in like a time step, or are they all like separately trained?
I mean, are you asking if it's end-to-end training in the end?
What exactly? Like go to the question, the figure with like the hops. If every F, like every network that will train, basically, it doesn't have to be, but
it's just a layer, like this word
so
layers.
it's every time it's trained separately. It's not you cannot parameterize like one network for all of them.
Are you asking if they have shared parameters?
Yeah.
No, they don't. So you have to start. It's not that it can't. So this is the normalizing flow. Here would be the simple prior, like the Gaussian. Here we would have like the complex, final distribution that that would basically resemble your optimal prior, like data-driven learned prior. Here in the normalizing flow, they would compute this data flow, right? So they don't really care. So for the evaluation, that's simple. That you just need the log determinant. They don't need to do sampling, so you don't have to sample from here. In this case, right? Why would you sample from here? You just sample from here, and then you just do the direct data flow. However, if you were to use these directly as your neural network to model your data, for instance, this is your Gaussian distribution, and this is your image, image layer. You can just use it, right? You can just use the normalizing flow, not as part of VAE, but to do maximum likelihood here, and this layer here would be your images. Then, like to sample for a new image, how would you sample? You have to have a way to go backwards, so that you can sample from the beginning. So then in that case, you need a transformation that is also easily invertible. The planar transformation and the rate of transformation, if you really check it, because I was trying to figure it out again, it's not that obvious how to check. Like it's not easy to find the inverse of this function. Although it's simple, looks simple, the inverse is not very easy to find, and I think in the original paper they don't even do it. Also in the original implementation they don't really do it with planar flows. This is easy, but the inversion is not easy, or at least not obvious. Is this clear what I mean, like what the distinction? Because for me it also took a bit, it's not so obvious when you read the literature because, well, things were happening simultaneously. But that's mainly the problem. There are like you can use normalize. So normalizing flows is a very nice and flexible way of defining densities. That's it. Like this is a density computer, let's say. Now, originally, this density computer was used. Their idea was, okay, I'm going to use it to minimize the gap of my elbow, right? Because if I have the optimal prior distribution, then my VA gap in the elbow disappears, and then I have perfect modeling, let's say, or as good as it gets. However, if you have the density, like a perfect density computer, you don't even have to go for a VAE type of approach. You can directly optimize your data. However, to do that, you need to have a method which is not only easy to compute the forward pass, so the log determinant of the Jacobian, but also you have to have a neural network for which it's easy to compute the inverse. So this requirement is theoretically needed anyways, even in the planar and radial flows, like with a VAE case, but there we just circumvent the problem. We just don't need to implement it in practice. That's the difference.
Why is it needed in theory?
Well, in theory you need it because, like when you're having normalizing flows, then in principle you want functions that you want to invert the function here. So in this direction you compute the forward, and this direction you compute the inverse function. However, like I mean, in principle, the change of variables can work in both directions.
Yeah.
But in practice, for the
if you're not going to use
exactly,
the reverse, then
exactly.
Yeah.
Exactly. So in practice, they didn't need to do it like for their original setting with the VAs. So why bother? Then you can have like something much more flexible, like the planar flows or not necessarily flexible, but something that for which you don't really need to compute the inverse actually. However, if you want to use these as a density computation methodology directly on the data, so that the last layer is not just an arbitrary distribution of some space that you don't really, it's just your prior, but if you want it on your image, then you need a way to go backwards, because when you compute density of your data, you need a way to sample from it also. And how do you sample it? Like I give you, let's say, a neural network with weights. How are you going to sample from it? If you have a Gaussian, you can sample. Like you can call numpy.rand n, and then you sample from it with, if you give them mean and average, so the mean and the standard deviation. But here, how are you going to do it? Yes?
I was wondering, why can I not, in this case, also sample from the left-hand side, the latent? Isn't that then mapped to the correct distribution in the image space? Or does it not work like that? Why do I need to sample from the right-hand side and not from the Gaussian?
You can do whatever you want for as long as you can have an easy version of the inverse as well as of the forward. It doesn't matter how it will. This is your data, which is your last layer, which is the stacking or the composition of these functions. Each of them is a change of variable functions. Each of them is a normalizing flow. Now this operation goes both ways. You can also inverse it. The change of variable still works. Basically, you're just shifting probability from one corner of your space to another. And in that case, you need a function. You don't need any arbitrary random function. You need the inverse of the corresponding normalizing flow. So if you want to go from one space to the other, from Z0 to Z1 now, you need the inverse. If you don't have that, you can easily go from Z0 to X, but you cannot go easily from X to Z0. Sampling means I sample from here and then I get something, whatever, like my data sample in the end, right? Going this direction would be evaluation. If I have now a new image, what is its right? So,
All right. Okay.
if you don't have something which is flexible in terms of computing the inverse, you can do sampling but not evaluation, or the other way around. You can do evaluation but you cannot easily sampling. If, however, you've got an easy way to do the sampling, the inverse, then you can do easily both. However, then you have to have the extra constraint that your neural network has to not only be easy to compute with respect to its local term Jacobian, but also the neural network has to be explicitly and easily invertible. And this is not obvious. How do you make a neural network which is invertible? And this was right. Yeah. Then this is basically they were learning better posteriors in the end by improving the priors, and then this making the gap disappear, the elbow gap disappear. So you could go from a Gaussian, like unit Gaussian, or uniform distribution. You could, like, with one flow you can change it to like this elliptical shape, or you can change it into two or more. But if you see, you never, I think, really create an absolute gap of zero. There's always a very small probability everywhere. So, and that can also be a problem, perhaps. But in general, when you by adding more and more like flows, you can have any type of distribution that you want. And this is for the radial transformation. So in a way, that's very flexible. To understand again the point of minimizing the prior, how would you write parametrically distribution that looks like that? It's not obvious, right? So it's much easier to have a uniform distribution, like we know the formula for the uniform distribution, we know the formula for the unit Gaussian, right? It's very simple. How do you, let's say that this is indeed our true prior distribution, how would you do it parametrically? That's very hard. That's the beauty of normalizing flows, that you don't really need to specify parametrically the distribution, you just let the neural network decide it. And now these are the flow-based models. So this is what I said. So far, the normalizing flows were already proposed for improving the prior in the VE. However, then it was proposed, what if we just use them directly for modeling data with the extra constraint that our we have invertibility, and then coupling layers was proposed. So with coupling layers, basically first is one instance of coupling layers. We're saying my input is Z. I'm keeping the same input dimensions, so I don't change them. However, for the remaining, I'm passing them through two neural networks, a mu and a sigma, which use as input the first half and modulated by the other half of my inputs. And well, if you do the like the computations, it's easy to derive that basically this is a triangular Jacobian and easy to inverse type of output for your flow. So this means that using a coupling layer for a normalizing flow, it was very easy to construct a normalizing flow that you can go for both forward and reverse, which means that you can directly apply this type of model for image data without having to do VAE type of formulation. It's easy to compute the Jacobian. The long determinant of the Jacobian here is just the sum of the diagonal here, because it's triangular matrix. The upper half is 0, so you can compute in closed form, and the inverse is also very easy, so you can go both ways. You can use it for both forward evaluation and for sum. Okay. And then all sorts of interesting extra steps or extra advanced methods were proposed on how do you split the dimensions here. I think originally it was half and half, but it doesn't have to be half and half. Maybe there are better ways. So using use of masking was proposed, like checker patterns or splitting across channel dimensions, or automating dimensions between consecutive layers. Anyway, like all sorts of different ways of splitting your dimensions were proposed for the coupling layers. And in practice like that, we were taking advantage of the, let's say, inductive biases of our data, of our settings. So for instance, when you've got images, like a checkers pattern makes a lot of sense, right? If you're having 2 and 3, you can easily compute 1 and 4, right? Much more easily than if you have one half and then you're asked to predict or to model the other, the second half. Multi-scale architectures were also then proposed so that you can, in a more engineering or practical way, how to. So that's the disadvantage of normalizing flows, that you have to keep the number of dimensions the same between Z and X. So how can you go deeper and deeper? Because de facto that's going to sort of make a problem with your computation. And multi-scale approaches were also proposed on how to reduce the resolution, basically by integrating out. And these were, let's say, for diffuse models, they were like the state of the art in image generation. So compared to VA, which was all very blurry, could see much nicer and crisper samples now. So another also point to realize here is that normalizing flows are continuous models, and they're very flexible, right? Like they're basically like clay. You can just, like the clay that you start from will always be there. The volume remains the same, but you can shape it to capture the precise shape of your data. And the problem with images is what? That they are discrete. So if you put something very flexible, a very flexible model on discrete data, then it will just focus on capturing these artificial bias, right? Like while the image is in reality continuous data setting. Images are continuous functions just because of the format that is available to us, the discrete format that is available to us. That would create a problem with normalizing flows that are, let's say, infinitely flexible. And then the normalizing flow would learn not to interpolate between the different pixel dimensions. It wouldn't really care if it's 0 or 1. Like the fact that 0 and 1 are next to each other, closer to one another than 0 and 10, doesn't matter. Okay, we just see these as discrete modes, as independent discrete modes. And that's not great. So a solution to that was adding noise, quantization, and variational quantization. So you're adding a bit of noise on your data. And then the model is not anymore, the data is not anymore discrete like that, but like it's like it captures the whole spectrum of data values. So the model is forced to be less biased. Of course, the question is, how do you add noise? You would like just add random noise, uniform noise, or whatever. I think in the beginning they were just adding uniform noise between the 0.5, basically, between the intervals. A better way of doing is variational dequantization, where you're saying that my noise distribution is a variational distribution, and then I'm learning the optimal variational distribution. Okay? I'm not going to go into more details because we don't have that much time, but this basically is the idea. It's important if you understand the basic idea. Yes?
Are you taking distributions from the discrete points and distributing it over the gaps, or are you basically filling in the gaps?
Are you, sorry, can one more time?
You go to the image. You put some value on all the discrete points, right? But are you so if you want to distribute noise toward between 0 and 1 to fill the gap. But like, do you distribute like part of the mass of the 0 and the 1 to fill this gap, or do you?
No, you just add noise, like that's it. Like we're talking about distributions here. This is a particular image, like a snapshot, let's say, like a particular sample, like in this image. But in practice, if that's your like the logarithm of your probability of your data x, then you're adding some noise here, x plus u. So you got some u noise, some random noise, and normally that would be uniform distribution. So in your image data, you just add uniformly between minus half and half on every pixel, let's say bit, every pixel value bit, like that's it. And instead of doing between minus half and half, you might want to say that I'm integrating over my noise variable to like just discover to learn the optimal noise distribution, and then you're optimizing for that.
Yeah, but then maybe I think it's really interesting. But like the noise, like why would you start with noise and try to learn this, and not maybe go for more like physics? Like there's many methods of physics to do this interpretation between. Why would you not start with something like this? It seems more obvious.
Well,
It seems
the
to-
initial idea was uniform distribution, so that's not physics-based. That's just like adding some like practical. It's the most practical problem, right? Practical solution, right? Like I see my probability density function, which is very flexible and capable of modeling any distribution of your data. If your distribution of your data is de facto biased due to some engineering constraints, for instance, the discreteness of values, then the flow normally would just pick on these bias. So the simplest solution is to add some noise, because that will not really affect your data, right? It's imperceptible. The pixel values don't really change with this noise. However, the flow does not really have any more bias to learn. How you add this noise in this practical solution? Well, initially it was the uniform distribution, because that seemed to be a reasonable and very simple choice. A physics-based approach, perhaps that will be also possible. I'm not sure what exactly you have in mind, but it doesn't matter. After that, variational dequantization was proposed as, let's say, the best possible way of learning this noise. So you just learn what is the optimal noise pattern, or the optimal noise distribution you would need to minimize a particular objective, or to maximize. You have to maximize some evidence lower bound with respect to that noise distribution. Physics-based approach is also possible. Any type of thing here would make sense. Of course, depending on the types of hyperparameters you're choosing. What was originally proposed was this uniform distribution, and then a variational way of finding the best possible anyways based on data. Is it clear? And one of our works with Philip and myself presented 2 years ago was on categorical normalizing flows. That's like a similar problem, like with discrete data. What happens when you've got categorical data? Because when you have categorical data, you cannot just add noise. If you have, for instance, let's say you're modeling distributions on variables that are colors, they're not forming a continuum. They're not just pixel values where 1 and 2 pixel intensity is closer than 1 to 10. If you have red and blue, they're not closer or farther away than red and yellow. Of course, I understand that the nanometers in light, so forth, you can say that there is something, you can derive some distance, but okay, let's say genders or whatever other, like there's all sorts of categorical data there. You cannot apply quantization, dequantization, noise dequantization. So in that case, here we're also proposing variational inference. So we're learning a continuous value to represent basically categories, something like clustering. So we would say, where is? You have like a continuous space here that you would like basically in the end cluster it, learn to cluster it such that this portion of the space corresponds to category 1, this one on category 2, etc. So we're converting basically a categorical problem into a continuous one with a variational inference and optimizing like that. It was not, so compared to standard normalizing flows, you will not compute the precise log likelihood anymore because you have to have variational inference. However, it was working pretty well on discrete data. We tried it at the time on, for instance, molecules, and well, with good scores. So normalizing flows, pros and cons. Starting from a very simple density, like a unit Gaussian, we can obtain any complex density that matches our data without even knowing its analytic form. So you have all the benefits. You can have very complex distributions, you can sample, you can evaluate, and so forth. You don't even need to know the precise formula. It allows for tractable density estimation in principle with efficient parallel sampling and learning. However, problem is that often you need lots of transformations. So you need lots of normalizing flow layers to capture complex densities. The reason is that the change of variable density works with very small, like the transformation have to be very small, so that to make this amenable. If the transformation is very large, if like the jump that you're asking the distribution change to make is too aggressive, then you won't be very refined in your final computations. We are constrained to invertible transformations with tractable determinants when we apply directly to data. In that case, with invertible transformations, it means that we have encoders and decoders that share the same parameters. Of course, there are two ways you can see this, as having more efficient models, because you're having the same neural network for both encoder and decoder. However, this also removes flexibility. Perhaps you would like to have better or stronger encoders, or stronger decoders, or weaker decoders, like depending on your data. With normalized flows, you don't really have the choice, the option to opt out if needed. And also with transformations, you cannot easily make bottlenecks. Your variables z1, z2, z3 up to zk, basically, and well, not ideally, but as per the definition, they have to have the same dimensionality as your data. You can go around this with engineering ways, but the basic principle remains. Before going to energy-based models, do you have any questions on normalizing flows? Okay, let me